with you guys, and we can recap a bit what we have learned last Thursday. And today we are going to have our last quiz, I believe, before I end my part. Right. So basically, last week we have went through several things. Example on power impedance. Okay. I've gone through the other types of design for electrochemical circuits. This is just to get you understand, and I believe what you have experienced during your practical is actually helping you in order to understand uh, the process of impedance, what kinds of information that we can interpret, and probably from the data that we obtain, what would be the equivalent circuits that we can use. Based on the data, we are able to interpret electrical components and whatnot. Okay. So other things that I have emphasized last week is basically on the difference between double layer capacitance or CDL uh, render circuit as compared to CPE, constant phase element. So I've told you that constant phase element is basically almost similar as renders, but the thing is the capacitance has been replaced. The double layer capacitance has been replaced with constant phase element capacitance. And this is actually with several reasons. Part of it is basically due to the data that we obtain. It actually experienced depression, or it actually experienced some abnormality where the Niki's plot or the semicircle plot is actually not a very round semicircle. It's more or less like a depressed. It's like, as I said, it's like a watermelon. You slice a watermelon because the watermelon is not actually round. It's oblong size or irregular size. So when you slice it into half, you see that it forms like a watermelon shape. This actually tells you that it experienced depression, and what caused depression is basically on the surface inhomogeneity. This is actually the main reason. Surface inhomogeneity due to probably a manual polishing. Okay, you do hand polishing. Okay, not polishing using a grinder polisher, or it can also comes from other reason, like for example the flatness of this the plate. If the plate is not really flat, then what happened is basically you will see that uh, the plate, when you polish it, some can be more exposed, the other part will not going to be exposed. So that actually caused the reason why we choose CPE, renders circuit. And other than that, regarding on Warburg, so Warburg actually happens due to diffusion, okay? And diffusion is actually related with a difference in concentration gradient, okay? That causes saturation, and when you have saturation, this actually triggers diffusion. And how to indicate Warburg impedance is actually very easy, because you will see that from the Niki's plot, it forms like a semicircle, and then after that, at the end, it forms like a 45 degree linear increase. So this actually tells you that you have some factors, a mass transfer factors, apart from charge transfer factors. So charge transfer is always going to be the semicircle, and then when you have diffusion, this actually can lead to a mass transfer effect. So basically, how does these things happen? I told you earlier that when you have saturation of concentration, especially on ions at the inner Helmholtz region, it will actually attract the other counter ions to go near, and the movement is actually due to diffusion, and the arrangement of the ions, the counter ions, is actually not uniform. It's like not forming like one layer, as what you've seen here. It's more or less like a finite size of arrangement, and this actually can trigger a diffusion layer or a diffusion resistance. So if you interpret this in the form of circuits, you will see that, okay, double layer still forming here. Charge transfer or polarization resistance is still there. And you have an additional of Warburg resistance at the outer hand pole switch. Just, on the tip of outer hand pole plane, and you still have a resistance of solutions. Okay, right? So the advantages and disadvantages of nickel spot. So this is actually quite important, because probably in your exam also I would like to ask this kind of things, what you can actually explore, what's the difference between nickel spot and border plot. So nickel spot is a plot between imaginary versus real. You will get it in the forms of semicircles and whatnot, but the disadvantages is because the frequency information is not given there. You can only see a frequency difference by means of border plots. Okay, right. So before we continue with equivalent circuit models for coating, I just want to ask, is there any question that you would like to ask from the previous lecture? Any question? Okay, all right. So if not, just want to continue. Well, when we talk about coatings, if you still remember, okay, get this one. Okay, so when we talk about coatings, you remember that coating is actually a layer formed on the surface of the metal, which actually separates the environment between the metals or the electrode with the environment. Okay, it creates like a barrier. So if you still remember how many types of I think coatings that we can have, if you revise back in chapter 3, anyone knows or still remember? Yep. You guys still remember? I mean, for coatings we have.
I remember organic and inorganic.
Organic, inorganic. Okay.
Metallic and non-metallic.
We can have, yeah, I mean, like metallic and non-metallic. So for non-metallic, it can be divided into organic and inorganic, something like that. Okay, just waiting for the pen to work on. Okay, that is still not working. Right. So as I said earlier, that for coatings you can have metallic coating. So metallic coating actually comes from what types of coating? So it can be electrode deposition, it can be electroplating. This part of the common techniques, if you notice. And for the non-metallic coatings, we can have like inorganic, which actually coming from the application of cement, concrete, ceramics or others. Meanwhile, for organic coatings, you can have like paint, you can have like application of tar and whatnot. So some of this coating is basically porous, okay, and some actually can be categorized as damaging coating. So damaging coating means that the coating is less stable. When you apply, normally it's just temporary and it can easily peel off or what. Okay, so that one actually we call it as like damaging coating. Okay, so in this case, you can have like undamaging coating. So undamaging coating, if you look from here, can anyone guess what would be the types of undamaging coating that we are talking here? Anyone knows? Or can guess? Right. So as what I told you for coatings, you can have metallic and non-metallic. Okay. So under non-metallic, you can have like inorganic or organic. Metallic, it can be from plating techniques, okay, deposition technique. Inorganic, as I said, the application of uh, ceramic coatings, concrete or cement. Meanwhile, for organic, it can be the application of paints, resins, or tar, whatnot. So undamaging coating is basically more or less related with it's actually related with electroplate. Deposition sample or others. But it's completely different with this one, metallic coating. So metallic coating, this one can be actually, metallic corrosion. This is actually for metallic corrosion. It's also related with non-coating. And also metallic coating. Okay. Damage coating over here normally happens if you have porous coating. Such example, paints, okay, and others. Well, for undamaging coating, as I said over here, this one is actually for deposition. Okay, deposition technique, electro deposition, okay, techniques, compared to other types of. So deposition is more stable. It's considered as undamaging coating. So that is why I think the equivalent circuit is going to be like as follows. Okay. So for damaging coating, I think next on we will look more on this. Okay. It actually produces a porous material. A layer that is porous. It can easily absorb water and oxygen. Okay. And that is why you have an additional of porous resistant and coating capacitors over here. Okay. Apart from charge transfer resistant and double layer capacitors here. And for metallic corrosion, this I told you for non-coating, okay, so metals that is not coated that we have seen in the past slides, and also for electroplating. Metallic coating is electroplating lah. Electroplating sample. Normally, the type of circuits we'll use is like this. And for electrochemical reaction coupled with chemical reaction, this is actually the examples. It can be even just to indicate that probably you can have a more complex structure of equivalent circuit whenever you deal with different kinds of samples. Okay. Any questions so far? Anything that you would like to ask regarding on this? before we go through the explanation. Diana, macam ada nak tanya je.
Ya, saya nak tanya. Yang electrochemical reaction coupled to a chemical reaction ni, yang bawah sekali, RT tu apa ya?
Sorry?
RT.
RP?
RT. Ta. RT. Depan
RT.
sekali.
Mana yang ni?
Yang tu. Yang tu.
Oh, okay. Nampak RT over here. So RT over here is actually a temperature resistance. Tapi this one is just an example, just to show that if you do any types of chemical reaction and at the same time you are measuring impedance, this is basically your resistance that you will get, because the temperature actually when you play around with the temperature, it will form like some additional effect to the data. So that is why you can also have like resistance temperature. Okay. So we take one examples for coating, right? Equivalent circuit for a metal coated with a porous non-conductive film. So you have a metal and then you apply paint on top. Okay. And then this is actually exposed. So you will see that over here, I mean, imagine that this is contained in electrolyte. Okay, so I told you that the oxygen in water can still penetrate to the layer of the paints, because this case it has a porous properties. Okay, so you can see from here, okay, RS, this is actually RS, and then the solution actually can travel, it can goes to the pore, travel, and this actually cause like a resistance, and we call it as pore resistance, RPO. Reason why it creates a resistance over here because electrons need to travel at certain obstacles to reach to the surface of metal. So that is why it creates an effect of resistance, and we call it as a porous resistance. And when it reach to the surface of the metal, the same process still happen. You still have a charge transfer resistance, and you still have a double layer capacitance. At the same time, the coatings also produce a so-called CCO, okay, or coating capacitance. All right. Cool. Okay. So if you actually draw the equivalent circuit, all right, so imagine that this here, and this is actually your electrolyte. So you have over here double layer, charge transfer, and then you have okay, you have a coating capacitance and porous resistance. RCT is RPO, is CDL, is CC code, and RS. Electrolyte is zinc, and this metal. So it's actually the interface between your working electrodes with your reference electrode. Okay, all right. So how does we know that this is actually a porous coating? I mean, based on EIS, how do we indicate? So all the while we are talking about the equivalent circuit, we have not seen what would be the border plot or the Niki's plot design. Basically, for porous coating, the border plot that you will observe is basically, it forms like three steps. One over here, another one over here, and maybe one here. It's low one. Cannot see. Okay. So this is just transfer resistant. Okay. And you have a porous resistant, RPO, and finally you have RS. Right. So if I cut this into half, okay, you know that this is actually at low frequency and this is actually at high frequency. Okay. So low frequency actually means that, low frequency means that the process actually happens where? At the inner hem holes or at the outer hem holes? If you still remember. Shamira? Tak tahu? Okay. Mahdi?
Yes, doctor.
Low frequency actually happens where? At the inner hem holes region or outer hem holes?
In outer,
Outer.
yeah, outer. No, not outer. In high frequency outer.
Okay. So remember, I told you that this is actually RCT. And if you still remember, oops, I think I don't have to draw again. It's already been mentioned here. Okay. So you have this kind of interface and you know that this region is actually at the inner hem host plane and this region is actually at the outer hem host plane. So inner hem host plane is actually region near to the electrode. Near working electrode. OHP, okay, region near reference electrode. Okay, right. So what will be the information that you get near the working electrode? Of course, RCT and CDM. So that is why over here, okay, the formation of RCT actually happens at the inner hem host region. Okay. Meanwhile, the information that you will get, okay, for example, like RS, RPO, this actually happens at outer hem host at higher frequency. Okay. So this is actually for border plot. A border plot, you will see that it forms like three flat lines. Three flat lines, which actually indicate that you will have like three capacitance. And furthermore, you can also notice that it has two slopes. So when you have two slopes, it means that you have two capacitance. Sorry, I did a mistake. It should be R, not C. Okay. So two slopes actually indicate that you have resistance. So of course, here is double layer capacitance, okay, CDL, and over here is the coating capacitance. So anyway, when you do EIS, if you notice that it forms like multiple steps, you count how many steps you have, like 1, 2, 3. You know you have 3 steps, or you have like 3 resistance. How many slopes? 2 slopes. So it means that you have 2 capacitance. And what about the the Nyquist plot. Of course, for the Nyquist plot, you will get like a 2 semicircle. Okay, all right. That actually indicates that this is actually RS. First semicircle. First semicircle is what? Anyone knows? It's equal to what? This is actually equals to RPO. And this is actually the second semicircle is actually equals to RCT. Okay? Is it okay to everyone?
Yes, okay. So far.
Okay. Right. So if you look from the Nyquist plot, I told you that it forms like a 2 semicircles. And even if you divide this into half, you can see that, okay, the first half of your Nyquist plot is basically at the outer Helmholtz plane, and the other half is basically at the inner Helmholtz plane. So that is why I think the first half on the left is actually you have RS and RPO. This actually happens at the outer Helmholtz plane. While for the RCT, it is actually happens at the inner Helmholtz plane. So in fact, imagine that if you have like an unknown sample, which you don't know what will be the sample, whether it has coatings or whatnot, then you can tell from looking at the Nyquist plot and also from the border plot. So this is actually the one that I've told you just now. So you can notice that over here for the Nyquist plot, you have like 2 semicircles. Okay. And then you can also notice that it has like 2 slopes, 1, 2 slopes, indicating that you have like 2 capacitance. In fact, for this one also shows like 2 peaks. You have like one here, another one here. One is over here, another one is over here. 2 peaks, capacitance peaks. Resistance 1, 2, another one here. So because it's run at this range, maybe if you run it bigger, you can see another flat line over here. Okay, but how actually we know that it has another resistance here? Because you can see that it is not starting at the origin, not at origin, not at 0. So means that it has some resistance, okay, some amounts of resistance, because from this scan is already forming quite huge number of resistance value. So it indicates that probably over here you have a resistance. Okay, right? So this is also another examples. If you have like equivalent circuit with an intact paint film, okay, types of border plot you will get is just maybe slopes. Well, some I think resistance can be indicated here. I told you probably values is not really visible, but clearly it's not start from origin, so you can have a resistance here and it stops here. So probably you can also have a resistance here. Semicircles or the Nyquist plot actually forming not a perfect vertical line, it's just like a tilted a bit, dia macam slightly like this. Then still we can say that it has a parallel effect, because for series is normally a very straight 90 degrees, and this one is not really 90 degrees, it's like slightly bent. Then you have like a parallel design. Equivalent circuit for coating that developing a low pore resistance. Low pore resistance, for example, sol gel. I think during your practical you have probably been introduced with sol gel coating. So what does it mean by low pore resistance? Okay. Okay. So low pore resistance actually means that the types of coatings that you apply actually produce a very thin film, very thin, almost invisible, okay, very thin, maybe less than 5 micrometer. So this actually create a low pore, because low pore means that it's highly conducting. Maybe thickness is very small, very small. Then the penetration of oxygen and water is assumed easy. So that is why it creates a low pore effect. Equivalent circuit with a freely corroding metal substrates. So this is actually almost similar like what we have seen just now. It has two semicircles, very small semicircles here, and then here. So that is why you have like still three resistance: RS, RPO, and RCT. RS, RPO, and this RCT. We have two capacitors. You have like one here and another one here, two capacitors. Equivalent circuit for a painted metal substrate that has suffered major damage. Major damage. So design is almost the same, but you can notice from the border plot okay, that the capacitance loop over here is more complete, okay, as compared to here. Here is like slightly skewed a bit. In fact, for this one is also almost complete. So this actually tells you that when you have an almost complete capacitance loop, this actually tells you that the coatings is actually suffer a major damage. Okay. So just a tips. Okay. Capacitance loop is more even because it is look more even. Shape is more even. So this actually indicate that coating suffers major damage. Okay, right. Any questions so far for this part? Anything? Nazira,
Hector,
okay?
as well as two shapes have the same Nyquist shape?
Yes, the same liquid shape. You mean for this one?
Yeah, the one and the previous one.
Still the same. Semicircle here, two semicircles. Yeah, almost the same. It's just that maybe from the border plot you can see that here it's more complete, the shape of this one. So it tells you that probably the coating is already been damaged. Okay. All right.
Okay, Doctor.
Right. So some
Thank you.
exercise. And this one is actually something that you can think. Maybe we can do it now. Okay. Can someone actually propose the equivalent circuit of this Nyquist plot? By looking at this Nyquist plot, can someone actually propose the equivalent circuit? So, as I said, maybe this part of the activity we can do. You just take a piece of paper, okay? You draw the equivalent circuit that you think will be suitable for this one, and probably within 5 minutes, I guess, you can guess. And then you just draw it on the piece of paper, snap it, and send to the WhatsApp group. And after that, we can actually look. Can you guys do that?
Okay, Doctor.
Okay, all right. So just take a piece of paper and then maybe look from here. You see that you have like, oh, I have how many semicircles and what are the effects that you have over there. Okay, so I guess maybe within few minutes while maybe I just proceed with the last part of the impedance. I mean, you guys just do it, propose it, and then snap the photo and send it to the WhatsApp group. And probably after this, we're going to discuss. So the modeling of any electrochemical system is complicated, and coated metals are at the extreme of complexity. There are several methods or models that occur during the life of a coating, and the most general one is shown in figure. In this model, RE is actually electrolyte resistant or resistant of solution. RC and also CC, which is the resistance and capacitance of coating. RP, which is the polarization resistant, or ICT, charge transfer resistant, which is inversely proportional to the rate of corrosion. Okay. CDL is the double layer capacitance at the electrolyte interface. So all the while when we talk about porous coating layer of impedance, this are the complexity that you will get. You will have additional information of resistance. At the same time, additional capacitance, which actually tells you this actually coming from coatings and others. So experiment setup for EIS is still the same as potential polarization and also linear polarization resistance. Yeah, I mean, almost the same as what you have seen during your practical. You will have like a 3 electrode system. Okay. And in this example, actually, the working electrode is being placed on the bottom. Okay. And the reference and counter electrode being put on top. Same for here. Okay. And the effects that actually affecting the electrochemical impedance measurement is also as follows. So this actually just a revision from chapter 1 and also chapter 4, chapter 3, which the electrochemical process will be affected by electrode variables due to like surface area, geometry, surface condition, whether it's polished or not, mass transfer variable, if the process is actually with aeration, with stirring or not. Solution variables due to the concentration of the electrolytes. External variables, temperature, time, pressure, and finally electrical variables. The setup of the potential values, whether it's potential static or not. Okay, current values and also a quantity of electricity or charge that you introduce. Okay. So before we move on to the electrochemical noise, is it okay to everyone? Already done with the part? Haven't seen any picture posted yet. You guys done with it?
One minute, Doctor. 1 minute.
1 minute.
Yeah.
Still. Okay. Yana siap dah?
Belum nak check jap.
Oh. Okay. Okay. Or not? Oh, okay. I got the first one from Mahdi. Okay. Mahdi, is it okay if I mean, copy your this one, your design, and then I put it here? Is it okay? I just draw.
Yes, Doctor. Okay.
Okay. And then I also have from Mira, Shamira. Oops. And then I have another design from Hamda. Yes, got it. Jihad, are you okay?
Yes, doctor, yes. I will just take a photo. Wait.
Maybe this one is CDL, I guess. Hamda. This one is RCT. Looks almost the same design. Nazira. Nazira also designed almost the same like Mahdi. Okay. And Liana. Oh, okay. Liana. Liana also the same as like Mahdi show. Okay. So the information that we obtain over here is that you have a two semicircle. It's mentioned here that you have a coating region. So the first point to here you have RS. The diameter of the first semicircle is equals to RPO. Okay, and then the diameter of the bigger one is actually still the corrosion region or the charge transfer process happens here. And finally, you have diffusion. You have wobble. Okay, right. So how do we actually translate this? Even though that you see that wobble is actually forming last because diffusion actually happens after it forms the charge transfer process. So, well, so basically, if you guys draw it like that, maybe I just you have reference electrode here. This is your electrolyte. Okay. So imagine that this is your coating, and then this is your metal. Okay, right. So, of course, the first one you are going to have RS, resistance and solution. You're going to have coating capacitance and also coating resistance, right? Okay. And then after that, what's next? Over here, you have double layer Okay, and then what? Ah. So over here, it should be resistant, and then you have another resistant, two resistant. So based on my drawings, maybe it's closer with this one, the one that proposed by Mahdi, Liana, and who else? But there's a problem. Over here, that you put the RP or RCT first. RS is here, putting capacitance is here. This RPO, porous resistance. This CDL. This one here should be what? Anyone knows? Over here, I think Mahdi and others put RCT or RP. Well, actually, this one is wobble. Okay, and this here is actually RCT. Remember that RCT is always near to the working electrode. Okay, and because of RCT have a saturation and everything, then it creates the wobble effect. So that is why besides RCT is actually wobble, but I told you that RCT must be closer to the working electrode. It cannot be wobble closer to working electrode, because actually what happened first is charge transfer first. Okay, and due to the charge transfer process, it creates a saturation, then only diffusion can happen. Okay, is it clear to everyone? Everyone get it?
Okay, Doctor.
Okay, Doctor.
All right. So this is actually the design. So probably later on in the exam, you already know, okay, this will be the design. So the other two, like this one, the other two design, this is actually a porous resistant coating. You can actually get this if you have two semicircles only, without wobble, without diffusion. Okay, so things that you need to highlight over here is that you have a diffusion or wobble impedance, okay, to be considered. All right. Okay. So we moving on to the other few last part before we end this topic. So the first one is actually electrochemical noise. So electrochemical noise is one of the technique as well. Okay, that is used to measure fitting corrosion. Okay, and this process actually a destructive process, which means you cannot actually reuse your sample after you've done the electrochemical noise. So what would be the measurements over here? You can, I mean, actually determine splitting by looking at fluctuations of current and potential. Okay. So this process or this method is also a transient method. Transient, what does it mean by transient? Transient means that a measurement over time. Measurement over time. So the data is actually recorded when you have like, if you say that you are doing, oops. Let's say that you are doing some measurement at definite time. Okay. So you are going to see the fluctuations of potential. Okay. and also fluctuations of current. So when you have a sudden change of potential or current value, okay, this is actually what causes pitting. All right. So various physical and chemical processes can give rise to potential and current fluctuations. These phenomena include pitting and crevice corrosion, uniform corrosion, coating failure, inhibitors activity, cracking, passive film stability, adsorption, and gas generation. The potential and current fluctuation from these processes are referred to as electrochemical noise. Noise signals may be required in several ways. Performing the experiment with two identical electrodes under open circuit condition with a zero resistant emitter or electrometer allows a measurement to be made with no external perturbation, closely simulating ambient real-world conditions. Both potential and current can be measured simultaneously. The fluctuations in potential and current can be analyzed to obtain information on the corrosion rate, types, and also characteristics. So as I said, for electrochemical noise, you can actually do it in 3 electrodes and also 2 electrodes. In 3 electrodes, you can have a pairing of working electrodes, reference, and counter, normal way. You can also have like 2 electrodes, working similar to working electrodes, like in the figure, okay, dip in reference electrode, 1 reference electrode. And you can also have like 3 working electrodes. But normally the one that we use in the lab is 3 electrode system where you have working, reference, and also counter. 2 similar working and 3 similar working electrode is, I think, for special types of experiment. The data that you will obtain is basically like this. It is actually from the actual data. You'll see that you have like a plot of current versus time and also potential over time. So blue is actually and green is actually potential. You can notice over here, okay, that at certain points, like for example, this one, this one, this one, this one, the one that I pointed, the one that you have some offset, probably it means that you have heating. Okay, and potential value at this value is not really seen much lah. I mean, in terms of the fluctuations. Okay, and maybe for this kind of data, you can see it clearly. You have a lot of fluctuations. When you have a fluctuation, it means that the current or the potential is not stable. So when it is not stable, then means that it is actively corroding, or maybe it's just like temporary, it starts to spike out. At some time it spike out. So this actually indicates that you may have a pitting or localized corrosion. Okay. So current have some fluctuations. The bigger the fluctuation is, okay, so the bigger the pit. Okay. So the theory of electrochemical noise is that from the natural voltage and the current fluctuation generated in corrosion cell, the derived parameters, voltage, okay, noise, and also the current noise can be obtained. This parameter can be used in Ohm law relationship to calculate noise resistance, Rn. So Rn is actually noise resistant. How you can get noise resistant? Okay, if you still remember for Ohm's law, okay, V is equals to IR, and if you want to calculate R, V is actually over I. So over here, it means that, okay, the noise resistance can be obtained if you divide the value of potential over value of current. So the thing is, when you do electrochemical noise, you will get a lot of data at different seconds. Okay, so what you need to do next is that you need to make a standard deviation values of your potential and also standard deviation values of your current, sigma. So the standard deviation of potential will give you one value. When you divide with standard deviation values of current, also one value, it will result you the noise resistance. So this information can be used to correlate with your other experiments that you did, probably LPR, or also EIS, because both this process actually produce resistance value, RCT, RP for linear polarization, and for EIS RCT. Okay, so you can compare in terms of the resistance value. If you have like one sample, okay, in acid, for example, then you can compare what will be the RP value from LPR, okay, what will be the RCT value from EIS, and also RN. Okay. No, it's almost going to give you almost the same, not really exact exact value, but almost the same value. So this actually indicates that the validity of the resistance value that you obtain from different measurement can be verified. Okay, the others is just examples or diagram to show the results of EN, or electrochemical noise. You can see that the signals showing from the figure top left, you have a lot of fluctuations in terms of potential. Okay. And in fact, from this sample also, you'll notice that it forms like a pitting, a huge pitting. So this pit. You see also here, small one, small pits. And what would be this one? Anyone knows what is this one? Can someone guess? It looks like a crystal, and this one may be NaCl, I guess. Sodium chloride. Maybe the tested solution is in salt solution. Then you will have like a crystal formation also. Okay. So the other observation that you can see, okay, there is potential over time, still the same. Okay. If you did the experiments at different times, different days, okay, sample, which means did several days, and then after that you do electrochemical noise, you will notice that at several days it can actually create pitting, because here probably from 3 days until 4 days, this is where passivity or passive layer already formed. So not much of fluctuation that you will see. But after that, you will start to see that day 6, you start to have like fluctuations. Okay. So it means that localized corrosion starts to occur. And then this is where you have your pitting. Okay. And after that, it starts to slow down again. It means that after the pitting have occurs, okay, 10 days, it starts to become stable. It means that the repassivation, okay, process occurs. Okay, so you have passive, okay, and then you have pitting and repassivation. Passive layer forms inside the pitting, inside the pit. Okay, other examples just to show the difference. I guess I will go to this in detail again. Okay. And probably if you notice, for this one, you have a carbon steel tested in soil and also with the presence of soil and also NaCl. So you can see that at different time of immersion, you can notice that the formation of or the corrosion rate values become fluctuates. Okay, at certain time, this is actually due to the formation of pitting, of course. So any questions so far for electrochemical noise before we move on to the last part, very final part? Any question from the floor?
It's clear.
Okay. The last part will be the advanced technique. So this one actually a new technology in electrochemical scanning. Okay. So in this process, actually, we will use the scanning techniques. You will give an image data, and the methods that we use for this one is called electrochemical scanning techniques. Okay. Or SECM, scanning electrochemical microscopy. Not SEM, SEM, scanning electron microscopy. So this one is SECM, scanning electrochemical microscope. Okay. So in this technique, actually, it uses a unique micro electrochemical techniques. It uses micro electrodes as probes. Okay. That provides in situ topography and electrochemical activity. So you will see like a topography, at the same time you will see the difference in potential and current. Information about the surface evolution at the micrometer scale in aqueous solution, thus becoming a very powerful tool in elucidating the complex processes occurring in the early stage of surface film degradation and metal corrosion. So as I said, this method is known to be a very advanced technique. Okay. So far in Malaysia, we have no SECM machine. Why? Because SECM machine is very expensive. Okay. So it's expensive, almost like a price of SEM. SEM, I think maybe if you can guess, it costs a few millions ringgit. So SECM also like that, because the most expensive part is not the potential step, but actually the micro electrodes, because it can measure in a micro distance. Okay. Right. So SECM is based in the reaction that occurs in the surface of mobile microelectrodes immersed in electrolyte solution. Okay. The microelectrode is rastered or scanned in close proximity to the solid surface to characterize the topography and the redox activity of the solid to liquid interface. Thus, the scanning electrochemical microscope can be employed for chemical microscopic imaging, which is especially relevant towards the investigation of corrosion and degradation processes, as well as to measure the activity of protection procedures of materials, right? So SECM measure the current flow or potential variation through a microelectrodes immersion, okay, in electrolytic solution and situated close to the substrate. The substrate can either be conductive, semiconductive, and insulating material. So in this case, actually, you have a metal surface, okay, and then your microelectrodes will be placed. So microelectrodes function like a reference electrode. Okay. Okay. So distance actually very near to the surface. So it will actually give a very precise data. And at the same time, these microelectrodes are mobilized. It can move from one side to another side. So it can scan. So it scans while vibrating from one point to another point. And then after that, it will produce like a topography. The main advantage of this method is their ability to detect, okay, and quantify the electrochemical activity of materials related to the onset of degradation reaction with spatial resolution. Okay. Electrochemical scanning techniques are based on principle upon the assumption that localized corrosion, where the anodic and cathodic processes take place at separate sites, can be represented as point sources. The electric field generated by sites of localized corrosion consists of equipotential lines which can be measured and graphically represented as a contour map. So if you notice this word, contour means that the topography that have an intensity in terms of color. Maybe if you learn geography before, you have heard about contour. Okay, it means that different intensity. Okay. So intensity of what? We are talking here intensity of current values or probably distance. So this is basically the setup. You will see that this is the microelectrodes. You also have like auxiliary electrodes and another supporting reference electrode being put over here. And this is actually your sample. Okay. So the probe itself consists of 125 micrometer diameter platinum wire seal with a glass tube of 250 micrometers external diameters, with the end polished flat to expose 125 mm diameters of platinum micro disc. Okay. And this will be the types of results that you can observe when you do SACM techniques. Okay. It actually produces a three-dimensional, image. Okay. So you have like current density over here. Okay. You have like potential, and you also have a distance value. In two-dimensional, maybe you will see that the sample is like this. Maybe you have like peak over here, but if you notice with scanning electrochemical microscope, it can actually measure your, peak. So this is actually pitting as observed from SEM. Right. So for SACM, it has a different methods or models. You can have scanning vibrating electrode technique, SVET, or as known scanning reference electrode, SRET. So SVET and SRET is actually the same things. It's just that over here, you will use a vibrating microelectrodes will be used. So the microelectrodes will be vibrated when it starts to scan. Okay. Right. So with this kind of things, it can actually give benefits. Okay. So the benefits of vibrating probe techniques, it can increase electrical sensitivity as well as enhance the system stability. Okay. All right. So the setup is almost the same. It's just that you have vibrating machine that is put with the microelectrodes and the probe here. So it will be vibrate, and then it will measure throughout the samples. So the information that you will see after that is that it will give a topography. Okay. So this is actually using SVET or SRET techniques. It will give a 3D dimensional. Okay. So probably with a normal measurement, you will see that there's a fluctuations, displacement over here. And when you did it like two-dimensional, okay, you'll see that there's a difference in intensity. Okay. And when actually you translate this into three-dimensional, so it means that you have current density, you have like potential, at the same time you have distance. The distance between the surface, the top layer with the bottom pits. So this actually will give you an image, a three-dimensional image. So this is actually measured using SEM. You cannot see anything. Maybe you notice some abnormalities here. But when you do scanning electrochemical techniques like SVET or SRED, you will notice that these actually have a higher current value, higher current density values as compared to the other parts. So it means that over here, it experiences localized corrosion. Okay. And finally, we have scanning Kelvin probe, SKP. Right. So SKP is a non-contact, non-destructive device for the determination of work function of conducting coated and semi-coated materials. Exploiting well the established principles of a direct correlation between the work function and the surface condition, it is a tool with wide application for both surface science and also industrial uses. Okay, so I forgot to tell you that for this kind of methods, the SECM methods, this method is known to be non-destructive because it didn't damage the sample. The sample is already been damaged, like it's already forming corrosion, but we just observe it. Okay? But the method itself of measuring, it's not destructive. Okay? So you still can use your sample for other analysis, SEM, SRD, or others. Okay. The difference between SKP and SVET is that for SKP, it's not a vibrating probe. It didn't use a vibrating probe. So that's actually the difference. Okay. Now, so we are done with our lecture, right? So before that, is there any question related on noise and also SECM? Anything that you would like to ask?
Okay, Doktor. Saya ada soalan.
Ya.
Slide berapa ni? Slide yang ada atas lagi. Ada beberapa noise. Lepas tu ada inhibitor.
Lena boleh cakap kuat sikit tak?
Oh, tak dengar. Sorry.
Tak ada apa? Slow.
Okay, dengar tak?
Which one? Okay. Yeah.
Okay,
Now, okay.
atas lagi. Dekat bahagian noise. Yang ni.
This one.
86. Yes. Yang bawah kiri yang ada inhibitor ni.
Okay.
Memang okay.
Kalau ada inhibitor, okay. So this one is actually if you add inhibitor lah, means that suddenly during the measurement or you add the inhibitor inside the solution or the electrolyte. It's quite unfortunate that this time we cannot do the practical for noise. I guess the previous years, I think I did the electrochemical noise experiment as well to study the effect of corrosion inhibitors. Okay, so basically, imagine that if you have current and also time, and when you do noise, okay? So this is actually probably the information that you get without any inhibitors, no CI. Okay. So when you add the inhibitors, normally you will see that it forms a very stable current values. And other things that you will notice over here is that when I overlay, the current value is not the same. Okay. For inhibitor, always the current is high. Current value is lower, okay, with CI as compared to without CI. Current is always higher. So when you overlay, you can see the difference. From the same sample, it's just with addition of CI or with CI. And there's no fluctuation. So this actually tells you a signal noise drops practically to zero, and the nucleation becomes to stand still after the addition of inhibitor. So when you add the inhibitor, okay, you will see that there's no more fluctuation. So no fluctuation means that the samples, I mean the metal will be like stable, and this is actually because of like the interaction between the corrosion inhibitor with the metals. So it actually prevent further corrosion process. So this is actually a clear difference that you can see from electrochemical noise. Okay, Diana?
Okay, clear, Doctor. Thank you.
All right. Any other question? Okay. So for noise, actually, of course, before we do it, we have to do OCP first. Okay. And normally the OCP will take longer time, maybe like 1 hour. Okay. Before we can run electrochemical noise. And the electrochemical noise is normally recommended for 1 hour also. So you have like OCP to make it very stable. Okay, for 1 hour, and then after that you do noise for another 1 hour as well. Okay. So with this, actually, you can observe pitting, or with OCP, actually produce enough time for passivity, okay, passive layer to form. And then another 1 hour is actually to see whether you can notice any pitting happen. Okay. So altogether, maybe per sample, it takes like 2 hours. So that is why I didn't do electrochemical noise, I mean, for your practical, because it's a bit time consuming doing that. Okay. All right. Any other question?
Okay, Doktor. Saya ada satu lagi soalan.
Yeah.
Okay, berkaitan tadi yang electric circuit model yang kita lukis-lukis tadi.
Okay. Circuit that we draw. Okay. This one?
Okay, this one. Okay, from the Nichols plot, kan kita tahu yang RS, RPO ni outer Helmholtz kan? And RCT and also Warburg punya inner Helmholtz, right? So from the Nichols plot, kita tak boleh consider like RCT tu lebih dekat kepada outer lah. Macam tu lah maksud dia.
Yes.
Kita tak, okay.
Exactly. Actually, if you look from Niki's plot, you cannot tell whether the RCT is located near to the working electrode or not. Because, as I said, diffusion will only happen after RCT. So, probably if you follow the flow like this, maybe you indicate RS will be first, and then after the RPO, RCT, and then Warburg. But as I said, Warburg only happens after you have saturation. So that is why RCT is always near to the working electrode. Then only you will have an effect of Warburg or diffusion.
Okay, Doctor. Okay. Thank you so much. Okay.
All right. Any other question from the floor?
No, it's clear so far.
Shamira, okay?
Doktor nak tanya, untuk Nichols plot ni, kalau kita nak plot, dia ada negatif, untuk imaginary impedance tu kena positif ke semua?
Untuk imaginary, sometimes you will notice that it can form negative tau. But it's very weird time lah. I mean, this off the lecture lah. Okay. Right. So, I don't know. Shamira ada experience ke buat impedance? Ada?
Apa ni? Daripada data lab hari tu, dia macam tu.
Yes. Okay. Alright. So, this is actually a very interesting thing. Yeah, maybe I afraid I have not gone through this lah. Okay. So imagine that this is 0. Your data is perfect semicircle, and then after that, you can see that it forms the other values. Normally towards the end, forming below 0, which means we consider it as negative lah. Okay. All right. and it forms like a tail over here. Okay? So this one we call it as a tailing effect of impedance. Okay, so what cause of this tailing effect? Normally pitting. So with impedance, I guess normally all the while we have not gone through whether it can see pitting or not. The answer is actually yes. When you actually do the measurement, you know that this is actually at the OHP and this is actually at the IHP. So the region at the last point is basically near to the electrode region. Okay? And if there's any abnormalities like tailing over here, or sometimes you do the semicircle and then it forms like a scattered points. Okay, scattered points is actually very easy to know. This is actually due to bubbles. Okay, bubbles forming on the surface of the electrodes or the metals. But for tailing, it forms like a tail. It goes inward like this. This is actually due to pitting. So this actually give rise to inductive effect. So inductive effect means that we have sometimes to consider the inductive element in our circuits. But most of the time, if it is too complicated, then I will ask the student to delete the point only. Okay, we just like select the points and then maybe we just delete it. So we just take until here. But if you want to explain the phenomenon, okay, this is actually due to pitting. Maybe if you want to put in a report or in the journal, if you have a tailing like this, then people will say that, oh, it's not a nice data because you have a pitting. Then sometimes you can omit it, or if you want to actually discuss on that, you can. So as I said, maybe in the equivalent circuit, you have to consider the inductive element. At the same time, you tell about pitting, the formation of pitting. Okay. All right.
Okay, Doctor,
Any
thank
other
you.
question? Any other question from the floor? All right. So I believe, as I said today, you are going to have your final quiz for today. So the quiz for today actually address cyclic polarization as well as impedance. Okay. And yeah, probably what you have learned so far, I mean, for impedance, you can actually apply it in your quiz. So yeah, I mean, hopefully you can answer. Right? If there's no further question, right, that actually marks the end of my part. Probably the following weeks, Dr. Faiz Bukhari will take over the lecture. Okay. And of course, we will decide on your test. I mean, as I said, your test is going to be online, and then the duration will be 2 hours. Okay, and we will do it via WebEx. I will share the dates later on once we have agreed with the time, because I have to check with the other two students who are a part-time student when they are free because they are working, right? But most probably I will plan it for weekends, maybe for weekends, right? So um, I wish you guys selamat Hari Raya. Okay. At the same time, I guess I will wish you all the best for your exams in advance. Okay. And hopefully, if you have any other things, I will start to evaluate your assignments and your quiz and everything. And probably before your exams, we can have like a tutorial session just to discuss about your assignments, your quiz, your tests, and everything before we sit for the exams, right? Once again, thank you very much. You've been wonderful during the class. I'm actually very happy to teach you guys. And if there's a further question, if you are a bit shy to ask during class, you can privately text me or else maybe you can email to me. So once again, thank you very much, guys, for your kind attention, and hope to see you in other time. Assalamualaikum warahmatullahi wabarakatuh, and goodbye.
Much, Doctor, for everything.
Thank you. Thank you so much,
Thank you,
Doctor.
Doctor.
Yeah,
Thanks for
welcome.
everything, Doctor. Waalaikumsalam warahmatullahi wabarakatuh.
Assalamualaikum.
Thanks.
Selamat Hari Raya, maaf lahir batin.
Okay, selamat hari raya to you too.
Eid Mubarak, Doctor.
Yeah, okay. Thank you, Hamda.